Okay, let's dive in. Welcome to the Deep Dive, where we tackle some of the biggest questions in physics and try to make sense of them.
And today, we're really aiming high. We're exploring the search for the ultimate laws of nature, focusing on this really powerful idea called supersymmetry, or SUSY for short. We're drawing a lot from the insights in Supersymmetry and Beyond.
Right, and to even start talking about where physics might go next, we have to talk about where we are now. That means the standard model of particle physics. If you're just tuning into this topic, you should know this theory is, well, it's often called the most complete mathematical description of reality we've ever had.
It really is an incredible achievement. The standard model, or SM, it describes all the particles we know, quarks, leptons, the stuff matter's made of, and the particles that carry forces like photons, W and Z, bosons, gluons. And it nails three of the four fundamental forces: electromagnetism, the weak force, the strong force. Decades of work went into this.
But, like any great success story, it has its limits, right? The sources suggest the standard model isn't the final word. It's what physicists call an effective theory. It tells us how things work incredibly precisely, at least at energies we can reach.
Exactly. But it struggles with the really big why questions. Why are the fundamental constants what they are? Why this specific set of particles and forces? It just doesn't say.
So it signals that there must be something more, something deeper, a final theory, maybe.
That's the hope. And our deep dive today is really about why so many physicists think supersymmetry is that next logical step, maybe the first step beyond the standard model, the first chapter of what you might call book 2. And crucially, it seems like the most promising avenue for finding new physics we can actually test in experiments.
Okay, so let's get into it. Why does this amazingly successful theory need help? Why isn't it enough? We've pulled out four fundamental mysteries the standard model just can't seem to crack on its own. Let's start with maybe the most technical one, the Higgs boson and something called the hierarchy problem.
Right, the Higgs. We found it. That was huge. It completed the particle lineup predicted by the standard model, explaining how particles get mass. But when you really dig into the quantum mechanics of the Higgs within just the standard model, it gets problematic. Conceptually, it's kind of a mess.
What do you mean a mess? We measured its mass, right? Around 125 giga-electron volts, GeV. That seems pretty concrete. What's the problem the theory has with that number?
Well, the problem is quantum mechanics itself. In quantum field theory, you have these virtual particles constantly popping in and out of existence in the vacuum. They interact with the Higgs, and these interactions contribute to its mass, what we call quantum corrections.
Okay.
The issue is when you calculate these corrections using just the standard model particles, they are enormous. They want to push the Higgs mass way, way up towards the Planck scale, which is something like 10 million billion GeV. Ridiculously heavy.
Whoa. So the theory predicts a monstrously heavy Higgs, but we see a relatively light one. That sounds like a big disconnect.
It's a huge disconnect. That's the hierarchy problem. To get the observed 125 GeV mass in the pure standard model, you need these enormous positive and negative quantum corrections to cancel each other out with almost perfect precision to dozens of decimal places.
That sounds less like physics and more like winning the cosmic lottery. It feels unnatural, like the theory's hiding something if it needs that kind of miraculous fine-tuning.
Exactly. It screams incomplete theory. So how does supersymmetry fix this? This is one of its most elegant features. Remember those quantum corrections from virtual particles?
Yeah, the ones making the mass huge.
They come from two types of particles: fermions, which are matter particles like electrons and quarks, and bosons, which are force carriers like photons. Now, critically, fermion loops contribute a negative correction to the Higgs mass, and boson loops contribute a positive one.
Okay.
If supersymmetry is a true symmetry of nature, then for every standard model particle, there's a corresponding superpartner particle.
Those particles.
Right. A partner fermion for every boson, and a partner boson for every fermion. And the key thing is, the superpartner's loop contribution to the Higgs mass is exactly opposite in sign to its standard model partner's contribution.
Ah, so they cancel out.
They cancel out almost perfectly. The positive corrections from bosons are canceled by negative corrections from their fermionic superpartners, called bosinos. And the negative corrections from fermions are canceled by positive corrections from their bosonic superpartners, called fermions. This cancellation naturally protects the Higgs mass from blowing up, keeping it small and stable without any absurd fine-tuning. It's built into the symmetry.
That is. Yeah, that's incredibly neat. A symmetry explains why the mass isn't astronomically large. Okay, that solves a major internal problem for the theory. What about mystery number 2, dark matter? This is more of a cosmic problem, right?
Absolutely. Astronomers look at how galaxies rotate, how galaxy clusters move, how light bends around massive objects. And the unavoidable conclusion is that about 80–85% of the matter in the universe isn't the stuff the Standard Model describes. It doesn't emit light, it doesn't interact electromagnetically, it's dark matter.
And the Standard Model just has no explanation, no particle that fits the bill.
Zero candidates. None of the known particles have the right properties, stable, heavy, interacting only weakly or gravitationally. The SM is completely silent on what makes up the vast majority of matter out there.
So how does LZY help? Does it just invent a particle for the job? That might sound a bit convenient.
That's a fair question, but it's not quite like that. See, supersymmetry doesn't just invent one particle arbitrarily. It predicts a whole set of new particles, the superpartners. Now, in most realistic SOE-SWI models, there's a conserved quantity, kind of like electric charge, called R parity. What this means, practically, is that superpartners have to be produced in pairs, and they decay into other superpartners. But the lightest one can't decay into anything else without violating this R parity conservation. So the lightest superpartner, LSP, must be stable.
Stability is key for dark matter.
Exactly. And calculations show this LSP would naturally be heavy and interact very weakly with normal matter, primarily through the weak force and gravity. Those are precisely the properties astronomers deduced dark matter must have. So the LSP isn't just tacked on. Its existence and properties are a consequence of the supersymmetric framework itself. It's the leading candidate for cold dark matter, predicted by the theory.
Okay, that's compelling. It's not just an add-on, it falls out of the structure. Let's move to mystery 3, unifying the forces. Physics loves unification, right? Maxwell unified electricity and magnetism, the Standard Model unified electromagnetism, and the weak force.
That's the historical trend, yeah. The dream is a grand unified theory, or GUT, where the strong nuclear force joins the electroweak party.
How does the Standard Model do on that front?
Well, it gets tantalizingly close. In quantum field theory, the strengths of the forces aren't constant. They change depending on the energy scale you probe. We call this the running of the coupling constants. If you extrapolate the strengths of the ultramagnetic, weak, and strong forces to very high energies, using just the Standard Model...
That'd be closer together.
They do. They definitely trend towards each other, which is suggestive, but they don't quite meet at a single point. They miss. It's like three lines heading towards the same destination, but just slightly off course, so they cross near each other, but not perfectly. No unification.
Okay. Close, but no cigar. So how does adding supersymmetry change that picture? It seems weird that fixing the Higgs mass would also fix force unification.
It does seem almost too good to be true, but it works beautifully. Remember all those new superpartners COE-Y predicts? They also participate in these quantum interactions, so they affect how the force strengths run with energy.
They change the calculation.
They change the slopes of those lines, essentially. And when you redo the calculation within the supersymmetric Standard Model, including the contributions from all the superpartners, the three force strengths converge almost perfectly at a single, incredibly high energy scale, around 1016 GeV. Wow. So the lines actually meet. They meet with remarkable precision. It strongly suggests that grand unification is possible, but only if nature is supersymmetric at some level. This wasn't guaranteed. It's a non-trivial success of the idea. It gives you this feeling that the math is pointing towards something real.
That's pretty powerful evidence. Okay, final mystery. Mystery 4, the matter-antimatter asymmetry. Why is the universe all matter and basically no antimatter?
Yeah, this is a big one. According to our understanding of the Big Bang, the very early universe should have produced almost equal amounts of matter and antimatter. But when matter and antimatter meet, they annihilate each other into energy. So if they were perfectly balanced, they should have all wiped each other out, leaving just a universe full of radiation.
Clearly not what happened. We're here.
Exactly. So somehow a slight imbalance must have developed very early on, maybe one extra matter particle for every billion matter-antimatter pairs. That tiny excess survived the annihilation and formed everything we see today. The question is, how did that imbalance happen?
And the Standard Model can't explain it.
It has some of the necessary ingredients outlined by the Sakharov conditions, things like interactions that violate matter-antimatter symmetry, but quantitatively, it just doesn't seem powerful enough. The amount of asymmetry it can generate falls short of what we observe.
So SUSY, again, provides the missing pieces.
It provides new ways to satisfy those Sakharov conditions much more effectively. SUSY introduces many new particles, new interactions, new ways for matter-antimatter symmetry, specifically CP violation, to be broken. These extra ingredients provide more robust mechanisms to generate that necessary tiny excess of matter over antimatter in the early universe. It offers a much more natural framework to explain why we live in a matter-dominated cosmos.
Okay, so we have four huge problems. Higgs stability, dark matter, force unification, matter asymmetry, and supersymmetry seems to offer elegant solutions to all of them. Let's get a bit more concrete. What is supersymmetry, fundamentally? What does it add?
At its absolute core, supersymmetry is a proposed symmetry that relates the two fundamental classes of particles we know, fermions and bosons.
Remind us of the difference.
Fermions are typically the matter particles, electrons, quarks. They have half-integer spin, like 12. Bosons are typically the force carriers, photons, gluons, WZ bosons, the Higgs. They have integer spin, 0, 1, 2. Supersymmetry proposes that the fundamental laws of physics remain the same if you could somehow swap every fermion for a boson and every boson for a fermion.
Swap matter for force carriers. That sounds radical. What does that imply?
It implies that for every known particle, there must exist a superpartner particle. This particle has the same properties, like electric charge, but differs in spin by 12 unit. And, crucially, they also differ in mass.
So every particle gets a twin, a slightly different twin.
That's the idea. For every fermion in the standard model, there's a corresponding boson superpartner. For every boson, there's a corresponding fermion superpartner.
And there's fun terminology for these, right? The slanguage of SUSY.
Oh yeah. The superpartners of the standard model fermions, quarks, and leptons get an S put in front. So the partner of an electron is a selectron. The partner of a quark is a squark.
Like the partner of the top quark is the stop.
The stop squark, exactly. And the superpartners of the bosons photon, WZ, Higgs, gluon, get ino added to the end. So you have the photino, the wano, pronounced wino, the xeno, the Higgsino, and the gluino.
So electrons, squarks, photinos, winos. It's a whole new periodic table almost.
It literally doubles the known particle spectrum, at least in the simplest models.
You mentioned earlier this relates to space-time somehow, something called soupy space.
Right. That's a deeper way to think about it. Supersymmetry isn't just a symmetry between particles. It can be viewed as a fundamental symmetry of spacetime itself. Our usual spacetime has 4 dimensions, 3 space, 1 time which we think of as bosonic dimensions. Superspace extends this by adding extra dimensions that are fermionic in nature.
Fermionic dimensions, what does that even mean?
They're not dimensions you can move through like space. They're more abstract mathematical dimensions related to the quantum property of spin. Thinking about physics in this extended superspace is where the fermion-boson symmetry naturally emerges. It's also why Studio Y is seen as a potential key to unifying gravity, which describes space-time, with quantum mechanics, maybe within string theory. It intrinsically links space-time structure with the existence of both matter, fermions, and forces.
But clearly we don't see these superpartners everywhere. A selectron doesn't have the same mass as an electron, otherwise atoms wouldn't work.
Exactly. If supersymmetry were an exact, unbroken symmetry, the sparticles would have the same mass as their standard model partners. We definitely don't see that. So whatever supersymmetry is, it must be a broken symmetry in the universe today.
Broken how?
We don't know the exact mechanism, but something must have happened, probably in the very early universe, that hid the symmetry at low energies. This breaking mechanism is what gives the superpartners their mass, making them much heavier than their standard model counterparts.
Which is why we need giant machines like the Large Hadron Collider to find them.
Precisely. You need very high energies to create these heavy, unstable particles.
Yeah.
That brings us to the hunt.
So how do experiments like the LHC actually look for these particles if they're so heavy and probably decay instantly?
Okay, so the idea is you smash protons together at incredibly high energies. If SU-Y is real and the particles aren't too heavy, you might produce a pair of them in the collision, maybe a pair of squarks or gluinos.
And these immediately decay.
Very quickly, yes. They decay through a cascade, shedding energy and transforming into lighter particles, until eventually every decay chain must end up at the lightest stable superpartner.
The LSP, our dark matter candidate.
The very same. So in a typical SUSY event at the LHC, you'd produce a pair of heavy particles. They'd decay into a bunch of ordinary standard model particles, like quarks turning into jets of particles, electrons, muons, photons, plus 2 LSPs.
And the LSPs, they just fly off unseen because they're like dark matter.
Exactly. Because the LSP interacts so weakly, it passes straight through the enormous detectors without leaving a signal. It's invisible to us, but it carries away energy and momentum from the collision.
So you look for missing energy.
That's the classic signature. The detectors are designed to measure the energy and momentum of everything coming out of the collision very precisely. If you add up all the energy you do see in the jets, leptons, photons, and it doesn't balance the energy that went in, and particularly if the momentum doesn't balance, meaning something invisible carried momentum away in a particular direction, that's a strong hint. It's missing transverse energy, or MET.
So you look for events with lots of particles plus a significant amount of missing energy. That's the smoking gun for CUAY.
That's one of the primary search strategies, yes. Finding events with lots of activity and large missing energy would be incredibly exciting. It could simultaneously signal the discovery of supersymmetry and the direct production of dark matter particles in the lab.
Which brings us to the ultimate payoff. Why is finding CUAY considered so crucial? You called it a window to the final theory. What does that mean?
It means it connects physics across vastly different scales. The LHC probes physics at energies corresponding to distances around, say, 1017 or 1018 meters. The final theory, whatever it is, maybe string theory or M theory, is thought to operate at the Planck scale, which is incredibly tiny, around 1035 meters.
An unimaginably smaller scale. We can't build a collider to reach that directly.
Not even close. The energy required is orders of magnitude beyond anything conceivable. So how do we test ideas about Planck-scale physics? This is where ABC becomes potentially essential. If supersymmetry exists and is broken around the energy scale the LHC probes, the TWEV scale, it provides a mathematical bridge.
A bridge how?
It allows theorists to take a fundamental theory like string theory, which is naturally supersymmetric and defined at the Planck scale, and calculate its specific consequences down at the observable TV scale. Things like the predicted masses of the different superpartners, their decay patterns, the properties of the Higgs boson. These become calculable predictions that we can test at the LHC.
So LHC results can constrain or guide string theory.
Exactly. Without CUAY, it's very hard to connect Planck-scale ideas to experimental reality. Supersymmetry, if found, acts as that vital window, allowing information to flow both ways. LHC discoveries could tell us which versions of string theory are viable, and string theory could predict what the LHC should see next. It makes the search for a final theory experimentally grounded.
And what if the simplest, lightest superpartners aren't found? Is that the end of the road for CUAY? There was talk of a nightmare scenario at the LHC.
Well, that term was used, but it's perhaps a bit misleading. The nightmare scenario basically referred to finding only the standard model Higgs boson and nothing else, at least nothing easily detectable. But interestingly, some of the more developed models coming from a compactified M theory or string theory actually predict something like this.
Really? They predict CUAY is hard to find.
They can, yes. In some scenarios, the squarks and sleptons, the fermions, are predicted to be very heavy, perhaps too heavy for the current LHC to produce easily, while the bocinos, like Higgsino, might be lighter but harder to distinguish from background noise. So even finding just a standard model like Higgs, while disappointing in the short term, could still be consistent with these deeper supersymmetric theories. It just means nature chose a version of CUSY that's tougher to uncover. The search isn't necessarily over.
Okay, that puts it in perspective. So wrapping this up, the search for supersymmetry isn't just about bagging new particles like Pokemon.
Not at all. It's about testing a fundamental principle that seems necessary to solve deep puzzles within our current understanding, stabilizing the Higgs, explaining dark matter, unifying forces, accounting for the matter in the universe.
And maybe most profoundly, it's potentially the only handle we have to experimentally probe the ultimate structure of reality at the Planck scale. It's the bridge.
It really connects everything, from the largest scales of cosmology down to the smallest scales imaginable, potentially within one coherent, symmetric framework.
Which leads us to a final, maybe slightly provocative thought for you, our listeners. Think about the history of science. For a long time, it felt like endless exploration, mapping new continents, discovering new species. But now, in particle physics and cosmology, we've pushed our understanding back to fractions of a second after the Big Bang and down to the fundamental building blocks of matter.
We've mapped a huge territory.
So here's the thought. Is it possible that these two fields, particle physics and cosmology, are unique in science? Could they be the only fields that might actually end? Not because we fail, but because we might actually succeed in finding that complete final theory that explains everything within their domain, from the quantum to the cosmos. Something to ponder.